Hi everyone, I am Dila and I'll be presenting my final year project on forgery localization in images. First, I would like to dive into image forgery detection. As technology is becoming more advanced, images can easily be altered with open source software, which makes humans question the authenticity of these images. There are two types of forgeries, which are information changing and information preserving. Information changing is used to change the content of the image, while information preserving operations are used to hide the thumbprints left by information changing. In recent years, only specific regions are tempered in the image and are then post-JPEG compressed to conceal the thumbprints further. Hence, my objective is to detect tempered regions in an image by dividing the image into blocks and identifying the forged blocks. The 10 information preserving operations that are used to temper the images are as shown. Multiple image forgery detectors have been implemented throughout the years. Even though the current state-of-the-art detectors show promising results, they face either of these problems stated in these slides. The proposed image forgery detector is based on forgery localization in images based on joint statistics of image blocks with neighboring blocks paper by Singh-Hals, which combats the problems mentioned earlier. The model will be trained on an 18-dimensional universal feature set to classify the image blocks as either fake or real. Before extracting features from the tempered images, the images will have to be pre-processed. The image in spatial domain is converted to residual domain, which suppresses the JPEG compression artifacts. Afterwards, zero padding is added to the boundaries of the median filtered residual images, which is also known as MFR. Without zero padding, the image blocks that are located near the edge of the image will not have the same number of features extracted as the blocks located at the center. This can lead to a compatibility issue during training. The MFR images are then divided into image blocks with sizes of 128 by 128, 64 by 64, 32 by 32. The joint statistics of image blocks with its neighboring blocks, which are maximum cross correlation and Euclidean distance, are extracted, along with entropy and variance. These features are then used to build the final feature set. The custom datasets are built on BAUS S2, BOSS base, IEEE public database, which are tempered on specific requirements. For experiment 1 dataset, the left region of an image is tempered with each of the 10 information preserving operations, which is then post-JPEG compressed with quality factor of 70, then divided into blocks. For experiment 2 dataset is built similarly like experiment 1, but the main difference is the images are post-JPEG compressed with quality factor of 30. For experiment 3 dataset is built to test the performance of the model in detecting partially forged blocks, as in practical scenarios, forgery can occur in any regions of the image. This diagram depicts the overall workflow of the proposed image forgery detector. The evaluation metrics that I'll be using for the experiments are as shown. The 3 experiments carried out will be trained on the custom datasets mentioned earlier. In experiment 1, the manipulation operations highlighted in green achieve high accuracy score and F1 scores in different sizes of image blocks. However, detection in images that are manipulated by JPEG 2000 operations scored low accuracy scores. This is due to double compression. Double compression causes a huge drop in the quality of images. In experiment 2, as compared to post-JPEG compressed tempered images with quality factor of 70, the accuracy score decreased slightly. As quality factor decreases, the performance of the model decreases. Similar to experiment 1, the model achieved low metric scores for images tempered with JPEG and JPEG 2000 operations. In both experiment 1 and 2, accuracy in detecting image blocks of sizes of 32 by 32 is the lowest. For experiment 3, the accuracy score in detecting partially forged image blocks for sizes 64 by 64 with quality factor of 70 is fairly high. Sample outputs are as shown for experiment 1, experiment 2, and experiment 3. With a significant rise in digital image editing software applications using image tempering operations, forgeries in images have evolved to deepfake. Hence, deepfake field is also explored in this project too. Due to a face-swapping technology, a scam victim had lost $805K to the scammer. With the use of deepfakes, an individual is able to impersonate anyone. Hence, many deepfake detection techniques have been implemented to detect deepfakes. However, existing detectors have its shortcomings, which are they are unable to detect post-JPEG compressed deepfake images, and they may also utilize high-dimensional feature set. The eyes, nose, lips plays an important role in deepfake, which will be leveraged in the proposed detector. Lenny Conrad's work, which uses simple machine learning techniques, will be the baseline for the proposed detector. The proposed deepfake detector will utilize the features extracted from each facial part to train independent random forest classifiers. The results will then be used to produce the final predicted class of the image. The eyes, nose, lips are first extracted from the image and are then converted to be in residual domain, which is used to suppress JPEG compression artifacts. The features extracted are based on Delaney Conrad's work. Variants are added in the feature sets relating to the research on image forgery detection. Each feature set are created and are used to train the random classifiers which produce confidence scores. Lead fusion technique is used to combine confidence scores in outputting the final predicted result. The dataset that is used to train the model is Kaggle Deepfake dataset, which is based on Open Forensic dataset. The diagram depicts the overall workflow of the proposed detector. The feature set that is extracted are then used to train 3 supervised machine learning models in the late fusion stage. Based on this experiment, the decision tree classifier produced the highest accuracy score and F1 scores. To mimic the practical scenarios, an application is then built on a combination of methods that were explored using Python tkinter to prove the usefulness of the research findings. The application offers image forgery detection and deepfake detection. In image forgery detection, tempered image is uploaded, the MFR is then retrieved, the sizes of image blocks are selected, features are then extracted from each block. Once completed, select the desired tempering operation to be detected, and finally identify the forged blocks. In deepfake detection, upload the image. Afterwards, the facial parts are identified. Convert these patches to residual domain and extract the features. Lastly, the application will then provide the predicted class of the image. In this project, simple machine learning techniques are proven to show promising results in image forgery detection and deepfake detection.